Let's talk about separable extensions. Okay, so this is a special property of field extensions, but before we talk about the extensions themselves, let's talk about separable polynomials. So this is a notion which you have seen already. This is just the idea of having repeated roots or not having repeated roots. So let me define it formally. Let f be a polynomial with coefficients in a field capital F. Let's say f is in fx. We say f is separable. This polynomial f is separable if it does not have repeated roots, if it has no repeated roots in any field extension of capital F. Okay, so in any field extension of K of F. Okay, and of course to check if, so suppose you're given a polynomial f, to check if it is separable or not is, well, where's the best place to check? If you, for example, take K to be, let's say, the splitting field of F. So suppose K is the splitting field of F. Or you take K to be, let's say, the algebraic closure of the base field capital F, definitely over which the polynomial F splits. Okay, so in fact you can take this or any field extension of F over which F splits completely into linear factors. Okay, so it's sort of enough to check. So you know, to check if a polynomial is separable, you just have to check whether it has repeated roots in this particular extension. Okay, and well, why is that? Because of course here F splits as a product of x minus, so into distinct, but not necessarily distinct, into linear factors completely, and if no two of the alphas are equal in K, then you can be sure that you will not have repeated roots of F in any other field extension. Okay, and well, what's the well, what have you seen before about polynomials with repeated roots? So recall we have a criterion. Well, there are two different criteria that you have seen in the earlier lectures. So to check if a polynomial is separable, you don't really need to go to some, you know, splitting field and check if you have distinct roots there. You can just do this checking without leaving the base field at all. Okay, and that's the proposition or the theorem. So recall the derivative criterion. We call the earlier proposition, which says that F has no repeated roots, which in our new terminology, F is separable if and only if the GCD, if you take the polynomial f and its derivative, okay, so what is called d of f, if the greatest common divisor of these two is just 1, okay, if these two are relatively prime, okay, i.e., so in this case, I mean, this notation is the ideal generated by f and df, but you can also think in terms of just elements, they don't have any common factors, i.e. f and its derivative df are relatively prime. Okay, and this is an if and only if condition. So recall the derivative here is the formal derivative of a polynomial defined by saying the derivative of x power n is just nx to the n minus 1. Okay, so I sort of encourage you to go back and look at the earlier lectures on repeated roots to recall the definitions and properties. Okay, now this was the criterion which tells you when a polynomial is separable. You just have to check if the polynomial and its derivative have a common factor or not, and this you can just do in the base field, right? This is just a calculation in f of x, just compute the GCD by, say, the Euclidean algorithm. Okay, and also recall a second way of doing this, so we won't really use this, but recall there was this notion of a discriminant discriminant of f. So this was defined as, well, you can just take the product of the various roots, let's say I not equal to j or I less than j, and take the square of the roots of the polynomial. So of course, as written, this is something which you can compute in the splitting field or the algebraic closure, because that's where all the roots are going to be present. But a priori the answer is in K, some splitting field, but we know that the function that we have constructed here is a symmetric function of the roots, and therefore this is actually will turn out to be some polynomial in the coefficients. It's a polynomial in the coefficients of the given polynomial of x. Okay, and here is the second criterion for separability. Recall f is separable, meaning it has all distinct roots, is the same as saying this discriminant delta does not vanish. Okay, so delta is not 0. And this is delta of f. This is some particular element of the base field, okay, which turns out to be some polynomial function of the coefficients. Okay, so this is another way of computing or determining if f is separable just by staying within the field of definition. You need not go to some splitting field. Okay, and of course you've probably seen a bunch of examples back in the earlier lecture when repeated roots were discussed. So here are some quick examples. If I take fx to be x cubed minus 1, for instance, and I think of my base field as the field of rational numbers. So this is a separable polynomial because, let's say, I go up to the algebraic closure. So this is the expansion over, let's say, the complex numbers. Okay, or you can take the algebraic closure of Q, it doesn't matter. So once you pass to some extension field and where it splits completely, there you can check. There, if it has distinct roots, then this is a separable polynomial. Okay, so here's an example of a separable polynomial, and here's a non-example of a separable polynomial, the very same polynomial, but considered over the finite field F3, where, as you know, it just splits as x minus 1 the whole cube. Okay, so this is the expansion over F3, and of course this is not separable because the root 1 is repeated thrice. Okay, great. So here are some examples and non-examples, and what will be important for us is again a fact that was proved during the earlier lecture on repeated roots. Recall the following proposition as well, or theorem, which says, gives you yet another criterion for separability, but this time for irreducible polynomials. Okay, so let f in fx be an irreducible polynomial, be an irreducible polynomial. In this case, separability is much easier. So let me state it as f is separable. F is a separable polynomial if and only if its derivative is not 0. It's not the 0 polynomial. Okay, recall the df, the derivative, is again a polynomial in fx. So what we are saying is that this polynomial df, so this is, recall, some polynomial in fx, this is not the 0 polynomial. Okay, so that is equivalent to separability, non-vanishing of the derivative. Okay, and recall this was proved sort of by showing that, by using the previous criterion, that separability is the same as f and df having a common factor, but df is of strictly smaller degree than f, and so they can't really have a common factor. If f is irreducible, the only factors of f are 1 and f. Okay, so if df has strictly smaller degree, there's really no way it can share a common factor with f unless df is the 0 polynomial. Okay, so that is how this was proved. Okay, so again here I'm referring back to the earlier lecture. And corollary is that in characteristic 0, if the characteristic of the field is 0, then the derivative can't vanish. So then every irreducible polynomial is automatically separable. Every irreducible polynomial f is automatically separable. Okay, why is this? Well, if you write out a polynomial, so when can the derivative can never vanish, right? So proof, if the polynomial f looks like a0 plus a1x and so on, plus some, let's say it's a degree d polynomial, a dx to the d, then the derivative df of x just looks like a1 plus 2a2 x plus etc d a d x to the d minus 1. And the only way in which this can be 0 is if a1, a2, ad are all 0. Okay, and here observe we are using the characteristic 0 hypothesis, because saying that some multiple of a2 is 0 is the same as saying that a2 is 0. Okay, so observe that the derivative can be 0 if and only if the following equations are true: a1 is 0, 2a2 is 0, 3a3 is 0, and so on. But then this is the same as saying a1 is 0, a2 is 0, a3 is 0, etc. Okay, because you can sort of cancel. So for example, 3a3 is 0 means a3 is 0. Yes, the field has characteristic 0. If the field had characteristic 3, for example, then 3a3 is 0 is always true. You can't conclude that a3 is 0 from there. Okay, so now where does this leave us? This says that this is the same as saying that f is a constant. Okay, this is like our classic statement from say analysis, which says that the only polynomials with derivative 0 are just the constants. Okay, this holds over characteristic 0 fields. But of course, a constant can't be reducible. Okay, if f is a constant, but then constants are not irreducibles, they are units. So this is observe in this case f is not irreducible. Okay, so the conclusion that we wanted, if f is irreducible, then it is automatically separable. Okay, so that's what we have managed to show, because if f is irreducible, then it can't be a constant. Okay, so that's a nice fact for characteristic 0, that irreducibility automatically implies separability. Okay, irreducible polynomials must have non-repeated roots, whereas the same thing is not true over characteristic p, as we just said. So let's now consider the next situation, which is what if f has characteristic p, if characteristic of f is a prime p, so p is some prime number here. Okay, so this is the positive characteristic case. Then this fact is no longer true. Okay, then it is no longer true that irreducibles are separable. Irreducible polynomials are automatically separable. Okay, so one has to be a little careful in arbitrary characteristic, and here's an example to show that one has to be a little careful when dealing with the case of finite characteristic. So let's take the field f to be the following. So I'll take f3, but I'll also adjoin this variable t to it. Okay, so what is f3 of t? So t is just some indeterminate here. So what is f3 of t? This is the set of all rational functions. So this is the field of rational functions in the variable t, which means it's polynomial divided by polynomial. So what are a and b? They are both polynomials with coefficients in f3, and the denominator is not 0. So b is not the 0 polynomial. Okay, so this is the field of rational functions. So it's a field, and it's in fact still a field of characteristic 3. It's a field of rational functions. Okay, so if you take any element of this field and you take 3 times that, then that's just 3 times a over b, but 3 times a is just the 0 polynomial. So f3 of t is still of characteristic 3. Okay, so it's a field of rational functions over the field f3, and this is still a characteristic 3 field. So I should say f is a characteristic 3 field. Now I claim that in this characteristic 3 field you can find irreducible polynomials which have repeated roots. Okay, what is an example? So here's the simplest example. Let's take f of x to be the polynomial x cubed minus t. Okay, so recall t is now, it's an element of the field, it's an element of f. Okay, so this is a polynomial of degree 3. X is the variable, t is like a constant. So well, claim number 1 that f is irreducible. Let's check this. So if f is reducible, then what can you conclude? Okay, so proof of irreducibility. If not, then well, it's a polynomial of degree 3, so it has to split into 2 pieces. Let's say it splits, it's not irreducible. Then at least one of the 2 factors must have degree 1. Okay, in other words, then there exists. So how does f split? Then f splits like this. Let's say f of x must split as some degree 1 piece into some possibly degree 2 piece. Okay, so degree of g is 2, let's say. So g may or may not be reducible, but I know for sure there is one linear term. And what is alpha here? For some alpha in the base field. The base field here is f3 of t. Okay, in other words, alpha looks like some a of t by b of t, some rational function. B is not 0, and so f of alpha is 0 therefore, right? Because f of x is x minus alpha into gx. If you plug in alpha equal to 0, what you're going to get, and if you plug in alpha for x, you're going to get 0. This just means that alpha is a root of the original equation, so alpha cubed equals t. Therefore this is going to give us a contradiction. This is like saying the polynomial at divided by bt, this rational function, when you take this and you cube it, it just gives you t. Okay, now why is this not possible? Because, well, let's rewrite it. It's at cubed equals t times bt cubed. Okay, and if you sort of see what these two sides look like, well, at cubed, a is, well, if you cube a polynomial, what do you get in this case? Well, a polynomial looks like this, right? At is some a0 plus a1t and so on. If you cube it, it's like the calculation we just did. I mean, we talked about this polynomial x cubed minus 1. So at cubed is just going to give you, well, a0 cubed plus a1t the whole cubed plus a2t square the whole cubed and so on. And then there will also be lots of cross terms, right? So when you do this expansion, you're also going to get 3 a0 square a1t plus 3 whatever a0 something and so on. But all the cross terms are all going to look like 3 times something. Okay, so these are going to be the cross terms in the expansion, and they're all 0. Why? Because this is, recall, everything is over the field f3 of t. So, or you can say that as we just observed, 3 times any element of f is just 0. F, the field f3 of t is of characteristic 3. So these terms are 0 in f. Okay, so the element at cubed in the field f just works out to be something like this. So this is a0 cubed plus a1 cubed t cubed and so on. So it's a polynomial which only involves the powers, t power 0, 3, 6, 9 and so on. This is at cubed, sorry. Well, the same thing holds for bt cubed. It's again going to involve only b1 cubed, t cubed and so on. But now I'm going to multiply it by t, because what I know is that at cubed is supposed to equal t times bt cubed. Okay, now you can see the contradiction, because now the right hand side has powers of t which look like t power 1, 4, 7 and so on. So this is all powers of t congruent to 1 modulo 3, and so these two can never be equal. Okay, there's just no way these two can be the same answer. Okay, unless of course all the a's and b's are 0, but we have assumed that b's are not 0. Okay, so that argument concludes the proof of irreducibility of this polynomial f. Now, it's easy to see that f is not separable. Why? Well, we already have a criterion for separability. If you have an irreducible polynomial here, so let's go back and look at our proposition. So what does the proposition say? If you have an irreducible polynomial, then checking separability is very easy. It's separable if and only if its derivative doesn't vanish. Okay, so we have already shown that this polynomial is irreducible, x cubed minus t. Let us show that its derivative vanishes. So let's compute its derivative. It's just 3x squared. Okay, recall the t is a constant here, right? So, well, the derivative is just 3x squared, but that's of course just 0 in the polynomial ring f of x. Okay, so the derivative here is just 0. Okay. So what does that imply? That says that this polynomial is not separable. This implies the polynomial f of x okay, which is exactly what we claim. So if you have a field of finite characteristic, then irreducible polynomials don't automatically become separable. Okay, but there is this one sort of nice exception or a special case when this holds. So those are what are called perfect fields.